In this unit, we're going to see how we can do inference in graphical models, how we can answer questions such as what is the marginal distribution of a certain subset of variables, or what is the so-called maximum a posteriori solution, what is the most likely configuration of random variables under that probabilistic model defined by a factor graph, for instance. And we're going to first look at inference in chain structured factor graphs. And what we are in particular going to look at is the so-called belief propagation algorithm, which is an algorithm that, depending on the order of the factors involved, can be quite efficient. In any case, it is much more efficient than just doing a naive calculation of, let's say, the marginal distributions, as we'll see. So here we have a simple chain structured factor graph. All the nodes are arranged along a chain with factors in between, and this is the corresponding probability distribution. Now, if we want to compute the marginal distribution of A, what we would have to do is we would have to take this expression and sum over all configurations of B, C, and D. What is the computational complexity of this? Well, if the variables are all binary, then we have 8 terms here. So we have 2 to the power of 3 equal to 8 terms, because we have 3 times a variable that has 2 possible states. So there's 8 possibilities in total. That doesn't sound too bad yet, but if you think about even a chain that is very long, let's say has 100 variables, then you already have a computational complexity of 2 to the power of 100, and it becomes really intractable to do marginalization with such long chains. And that's not really a large problem even. If you think about images that have maybe 1 million of pixels, it's clearly infeasible to do such a naive strategy for computing, for example, a marginal. So what we're going to do instead is we're going to use a little trick. And for doing so, we're going to observe the following. If we take this expression here and we want to compute the marginal of A, B, and C, which means we want to sum over D, we observe that not all of the factors involved in this expression depend on D, but only the last 2 do. Therefore, we can pull this summation operator inside that expression, or we can factor out these 2 factors here in front of the summation operator. And so what we're going to do here is we're doing the summation over D of just this expression here. And if you look carefully, this expression is a function of C only, because D is marginalized over, so the only free variable here is C. And we're calling this expression, the entire marginalized expression, a message that's sent from variable D to variable C, and that depends on C. So it has an argument C. You can think of this as a vector. In the case of binary variables, this would be just a vector of dimensionality 2 that has 2 elements, one for C equals 0, one for C equals 1. So we're calculating that vector, only that vector. And then we can do the same thing for C. So the marginal over A and B, what we have to do is we have to take this expression and sum over all possible states of C. And we observe again that the first factor does not depend on C, so we can pull that summation inside, and we can only do this calculation here, which again is a message. In this case, it's a message. We call it a message sent from C to B. And this is a function of B only, because all the other terms have been marginalized. And then we can simply recurse further. We can now compute the marginal of A by just summing over B. Now, B, the sum over B cannot be pulled in further, as we can see here, because the first factor already depends on B as well. So this is directly giving us the result. So we have now this expression here, which we can call a message sent from B to A, that is a function of only A because we have marginalized B. In other words, the message, we call this message mu, sent from M to N, from variable M to variable N, and that's a function of N, carries the information beyond that variable M. It summarizes the information and carries it beyond. So what did we gain? Well, if we look at the computational complexity now, what we can see is that we have now just done a summation of 2 terms here, a summation of 2 terms here, and a summation of 2 terms here. So we have a computational complexity of 3 times 2, which is 6. So 6 is not horribly much better than 8. But again, if you now think about very long chains where you may have 100 or more variables, then in this case, this would be 100 times 2. So we would have to do 200 operations, while in the previous case, in the naive case, we would have to do 2 to the power of 100 operations, which is more than there are atoms in the universe, so it's completely intractable to do. So for this very simple example, it doesn't play a big role, but as soon as the chain gets longer, as soon as it has 10, 20 variables, already for 10 variables, we have 1,000 operations versus 20 operations. So one grows exponentially and the other only grows linearly. However, we didn't need the factors yet. So we have a factor graph, but we didn't use the factors yet. But we will see that making this distinction is actually quite helpful. If we go to more complex structures like tree structured graphs, or branching graphs. So here, this is not a chain anymore, but now we have a tree. And now it becomes useful to have these factors because now we can collect this information also at the factor level and then spread it further from the factors, and so it becomes easier to describe mathematically. So this is a factor graph, a tree structured factor graph, and the corresponding factor representation here, or factorization. Now, how can we compute the marginal of, say, A and B? This marginal distribution over A and B, of this distribution over A, B, C, D, E. Well, the idea is the same. We compute and pass messages, but now not just between variables, but between variables and factors, and from factors to variables. So we're sending messages from variables to factors and from factors to variables. And this is what it looks like. So we have, for instance, a message sent from this factor to this variable, and a message from this variable to this factor. And this factor now collects these two messages and sends them further. And again, we're exploiting this idea of dynamic programming, of pre-computing results, or mathematically speaking, of pulling the summation term inside in order to gain efficiency. So let's do it concretely now for this tree structured graph. If we want to do the marginal, compute the marginal of A and B, then we do the same thing as before. We need to sum over C, D, and E, and then these terms can be pulled inside depending on the variables that these individual factors depend upon. So we define this entire expression as the message of F2 to B, because the only free variable here is B. And then this message can be split further by pulling in the E summation, because these 3 terms here don't depend on E. And so we come up with this message passing scheme where we send a message from D to F2 here, and then from C to F2. From C to F2 is actually very simple because this message here only receives information from a single factor. So this random variable here is connected only to a single factor, so it's the factor itself. And then we have the summation over C and D of this factor multiplied with these incoming messages, with these 2 incoming messages, the message from C, this one here, and the message from D, this one here. So we take a summation over the entire state space except of the variable that we're sending to, just C and D, we're summing over. But all combinations, in this case, this would be 4 terms, because if we have binary variables, because we have 4 possibilities for C and D. And we do this for the factor multiplied with the incoming messages. So this is repeated from the last slide here. If we now want to make this a little bit more general, what can we see here? Well, we can see that at a general level, more generally speaking, what we have is that a message that's sent from a factor to a variable and as an argument has the variable is simply a summation over the state of the variables that are involved in that factor. So here in this case would be B, C, D, except for the variable that we're sending to, except for B. This is excluded here in this summation. B is not part. This is indicated by XF without X. So this is a summation over the state space of all the variables except the variable that we're sending to. And the summation is over the factor itself and the product of all the incoming messages. So you can see here that these are all the messages that are sent to that factor that we are considering sending a message from. So we want to send a message from here to here. So we're considering all the messages that are sent to that factor except the message that could be sent by the variable B. So here we have excluded the variable that we're sending to from the set of variables that we are receiving messages from. The messages are only from the incoming side, not to where we send. That's important. So that's why it's excluded here. So we have a product here over the neighbors of F except the variable they were sending to, X, in this general notation. And we're distinguishing these 2 types of notations because here this is a summation over a state space, and here this is simply a product over a set of variables here, where we're misusing a little bit notation because we're using it also here as an index of the message. So we're using it as an index of the message and as the variable itself, just to not clutter the notation too much. But I find this the most clear exposition of this admittedly quite complex material. Okay. So, and the other side is, this is a message that's sent from a variable to a factor. In this case, from this variable to this factor, we have simply a product of the incoming messages. So we have a product of this message and a product of this message here, as we can see. And so in the more general form, this can be written as a message sent from a variable X to a factor F. That's a function of X, or a vector in the states of X, if you will, in a discrete case. And this is simply a product of all the incoming messages, where incoming means that we have chosen the factors such that they are neighbors of the variable X, in this case here D, but we are not considering F2, just F5 and F4, because we're sending to F2. So exclude again the factor that we're sending to in this calculation here, in this product. Admittedly, there's many subscripts here and it's easy to get confused, and that's why we have an exciting exercise for you to practice this and to get a deeper understanding. But it's important to look a bit at these slides and to understand how indexing works here. Once computed, this is the keep message. Messages can be reused. And an important observation is that all the marginals can be written as function of messages. And now we simply need an algorithm to compute all the messages. We have given some very concrete examples so far for computing very specific marginals, but of course we want to more generally have an algorithm to compute all the marginals, all possible marginals, let's say, at the same time, ideally. And for marginal inference, this is the so-called sum product algorithm. We're also going to get to know another algorithm, which is called the max product algorithm. But this is solving a different problem, the map problem, the maximum a posteriori problem, finding the best possible configuration of variables. Here we are looking at the marginalization problem as an inference problem, and this is solved by the sum product algorithm. So It's also called sometimes belief propagation because we're sending these messages on this graph. And it's an algorithm to compute these messages really efficiently, to avoid this exponential complexity that we discussed in the beginning. At least if the graph is not complicated, if it has maybe just pairwise potentials or not too high order potentials. And belief propagation assumes that the graph is singly connected, so there's no loops. It's either a chain or a tree. But we'll see that this can also be generalized to loopy graphs if we let go some of the guarantees, in particular the guarantee of exactness. If we are happy with an approximate solution, which often is good enough, then we can also apply this algorithm on loopy graphs. And the algorithm works as follows. We initialize in the first step, then we send variable to factor messages, then factor to variable messages, and we repeat this until all messages have been calculated and the algorithm is converged. And then we calculate the desired marginals, which is the goal of the sum product algorithm from these messages. So let's look at these steps in more detail. In the first step, this is the initialization step. The messages from the extremal node factors are initialized to the factor themselves. So here's an example, the message from the factor to the variable. If this factor is, is the end of the graph, basically, then this message here is simply, if there's no other variables connected to that factor, then this message is simply the factor itself. And that's easy to see if you look at the equations from the previous slides. And the messages from the extremal variable nodes to the factors is set to 1, but they don't really matter because they get updated directly with the algorithm in the second step. Then the second step of this algorithm is the variable to factor message computation. We have already seen the formula. It's simply computing the product of all the incoming messages. And here's an example. We have this variable that wants to send a message to this factor. So we want to calculate this message here. And this message is the product of the incoming messages, but not the message that's sent from that factor to X. Of course, we are computing messages sent in all directions, but for computing this message, this update here, we only consider the incoming ones to be mathematically correct, as we have derived from the simple example that we've shown. Now the factor to variable message has this form, as we've already seen, and this gives also rise to the name of this algorithm, the sum product algorithm, because we have a sum of a term that involves products. So to compute this message sent from the factor to this variable, we go over the entire state space over all y1, y2, and y3, except for the variable that we're sending to. This is excluded here. And we compute the value of this factor multiplied with the value of the incoming messages that are also functions of these variables. And then we're sending this to this variable. And then finally, once we have done this algorithm, we have applied this algorithm and it has converged, then we can read off the marginal distributions by simply taking the product of all the messages coming into a particular variable. Now, in this case, the difference here, unlike in step 2, is that here we calculate the product of all the over all the neighbors. So there's no factor that we're sending a message to. So we are taking all the incoming messages, in this case, the product of. And then we know that the distribution must be proportional to this. It's not normalized. There's no guarantee for normalization here. But because we're getting out a vector, it's easy to normalize that vector to 1. And that we can do in post-processing. Now, a few words about numerical precision. In practice, what we do for very large graphs is to use a so-called log representation, because in very large graphs, we, as you have seen, have to compute products over many messages And if these messages are smaller than 1, then they might become suddenly very, very small, or if they are bigger than 1, they might become very large. And this leads to numerical problems when storing these messages in a computer as floating precision or double precision numbers. And the solution to this is to instead work with log messages. So instead of working directly with the messages mu, work with the messages lambda, which are the logarithm of mu. And if we do this, then the product, for instance, in the variable to factor messages turns to a sum. And of course, a sum is much easier to work with. It doesn't have the problem that small numbers get to 0 very quickly because we're just summing up terms here. So it's better to work with, and that's what you will have to do if you work with reasonably sized problems and apply this algorithm to it, just because a computer has fixed precision or limited precision. Yeah, and so similarly for the factor to variable messages, they then become they look slightly more ugly here. So because we have the logarithm now, we have and the logarithm of a sum doesn't simplify further, so the logarithm remains here. But inside here, this message is replaced by lambda, and we have the exponential of the sum, because the exponential of this sum is the product of the exponential of this expression. And because we have chosen this as the logarithm of this, this is equivalent, right? So it's just the same. Now this was the sum product algorithm for computing marginals. We do message passing in both directions, between from factors to variables and from variables to factors. And once the messages don't change anymore, once the propagation has happened along the entire chain or the entire tree, we can read off the marginals as discussed. Now there's a second algorithm called the max product algorithm, which is very similar but tackles a different problem. The goal here is that for a given distribution P of A, B, C, D, we want to find the most likely state. We don't want to find a marginal, but we want to find, here illustrated with this argmax notation, we want to find the A star, B star, C star, and D star, which are maximizing this probability distribution. I want to find the argmax. And this is called the maximum a posteriori problem, or map problem, or if we find it, it's a solution. And it's called maximum a posteriori because we're doing this inference on a graphical model where, through the specification of this graph and the relationships in that graph, we have specified our prior knowledge. So we are finding the most likely solution after integrating our prior knowledge into the problem. That's why it's called maximum a posteriori. We are maximizing the posterior. Again, we use the factorization structure to distribute maximization to local computations as before with the summation. So again, an example for the chain here, and we can go a little bit more quickly. So it's exactly the same with the maximization, where we observe that some of these factors here don't depend on some of these variables. And so, for instance, the D can be pulled inside, and then we call this a message sent from D to C. Similarly, a message from C to B and from B to A, and so on. Now, what we do with this algorithm actually is we obtain the maximal probability value. But that's not what we were after. We wanted to know the most probable state. So we haven't arrived at the goal yet. And the solution to obtain, so this is only the first step. The solution to obtain the map state is that once the messages are computed, we can find the optimal values by backtracking. So we can find now backwards here the optimal A by maximizing this message that we have computed. And then once we have found the optimal A, we can plug that in here, and we can go one step backward and find the optimal B by maximizing this expression and recurs further backwards then. And this is called backtracking or dynamic programming, or in the case of Markov chains, also called the Viterbi algorithm. Maybe you've heard of this before. If, however, the maximum is unique, then the map solution is the maximum of the max marginals. And that's much easier to compute because we need to just find the maximum of the computed vector per variable. So we run the max product algorithm that's similarly defined to the sum product algorithm, just with a maximization instead of the summation. And then after running it, we obtain a vector at each variable. And that vector is called it's not a marginal because we didn't run the sum product algorithm. So some people call it a max marginal because it's kind of the marginal of the max product algorithm, despite the fact that actually marginal is not correct. But let's call it a max marginal. So for these vectors that we have obtained after running the max product algorithm, we can then just go through each vector individually and find what is the maximal value and then pick that state. So for binary variable, let's say if the second entry is larger, then the state of that variable is 1. And if the first state is larger, if the first entry is larger, the state would be 0. So this is much easier now because we can do this for each site. And in most cases, the map solution is unique, so we can do that. Okay. So the algorithm in this case is the same as before. We initialize, we compute variable to factor messages, factor to variable messages, and we repeat this until all messages have been calculated, and then we calculate the desired map solution. I haven't specified the individual steps here because they are completely analogous to the sum product algorithm, and I have summarized them on the last slides of this unit to help you also with the implementation of this algorithm. So all the information is there. Now, what we have assumed so far is that the graph that we consider is either a chain or a tree, but it doesn't contain any loops. However, in computer vision, many problems actually have loops. If you look at a simple image grid, like this 4-connected structure that we've discussed in the beginning of the lecture, then of course there's loops in this graph already very early on. If you just look at a very local part of this graph, you have loops. And so these assumptions that we have made in order to get an exact solution actually break. However, of course, the messages are well defined also for looping graphs. So we can just try to apply the same algorithm that's exact for trees and chains to loopy graphs, and that's called Loopy belief propagation. So we can apply the same algorithm to loopy graphs as well. But the downside of this is that we now lose exactness. So it's only an approximate inference. And in some cases, there's even, if in the simple case, in the simple algorithm that we consider here, there's even no guarantee of convergence. So it might actually diverge or oscillate. But often, for many problems in computer vision, this works surprisingly well, despite these violations of the assumptions. Now, well, the question is, what if we have such a loopy graph, how should we actually pass the messages? And typically people either choose a random or a fixed order. And a popular choice is that we first pass, because it's a bipartite graph, all the factor to variable messages, and then we pass all the variable to factor messages, and we repeat this for n iterations until we hopefully converge. Again, there's no guarantee of convergence, but we hopefully converge. And so an advantage of this strategy is that there's a lot of parallelism that can be exploited, because all the messages that are sent from factors to variables can be computed in parallel. So it's easy to parallelize this algorithm. So here's a summary. And these slides mainly serve as a guide or to help implementing the exercise task, where I try to make everything concise on a few slides describing the entire algorithm. The goal of the sum product belief propagation algorithm is to compute marginals of some distribution by passing factor to variable messages and variable to factor messages, as we have seen or derived before. To avoid very large values, what you can do is you can, in addition to the log representation, which you should always use and which is used here, subtract the mean of the messages after the message update in equation 2 to keep them around 0. And similarly, here the equation for the max product belief propagation algorithm, which computes the most likely state, where now the variable to factor message hasn't changed, but this message here has changed and the sum has been replaced by a maximum. In the special case of a pairwise MRF, this simplifies further, and that's the case that you're going to consider in the exercise. So here, for instance, the unary factor is simply the logarithm of the factor itself. It's easy to see this because, well, there is no other variables except for the variable of that factor. So the summation goes away, and also these terms here disappear because there's no neighboring variables of that factor that are not the variable that we consider. But also the pairwise factor simplifies because now there's only one neighbor, so we have to just sum over the states of y, which is the neighbor, if we want to send from f to x. And we have just this one incoming message that comes from y, that arrives from y at factor f. And the same for max product BP. And then at the end, we have the readout stage where we read off the marginal or the map state at each variable, which is similar to the variable to factor message, except that we sum over all the incoming messages. So this is done here for the marginal, and because the output here is not normalized, we have to normalize it in the end. You can see that we have an exponential here because we're considering the log messages. So of course we need to first convert this into probabilities. And then here on the right hand side, this is what we called considering the max marginals. So we're taking these so-called max marginals here. This is the sum over these log messages. And then we find the entry that is largest in that vector. And this is a very generic overview of the algorithm. The input is the variables and the factors that are specified. This is the definition of the problem. We allocate the messages in this log representation. Then we initialize the messages to 0, let's say, which corresponds to a uniform distribution, but you can also initialize differently. And then for some iterations, we update all factor to variable messages, all variable to factor messages. These are these equations from the previous slide, color-coded. And then we normalize them by subtracting the mean. And in the end, we read off the marginal and map state